In this video, we'll run a simple logistic regression with one continuous independent variable using the Youth Cohort Study of England and Wales 2004 to 2007 Cohort 12 dataset. This dataset is available for free download from the UK Data Service website. Let's say we wanted to answer the following question. What are the odds that young people with high GCSE scores in Sweep 1 of the Youth Cohort Study will be enrolled in full-time education in Sweep 2? Our variable of interest is S2Q10, a measure of enrollment in full-time education in Sweep 2 of the Youth Cohort Study. It is a binary categorical variable, meaning that it has two categories. This means we can model it using logistic regression, which requires a binary variable as the outcome or dependent variable. Because we're interested in the influence of GCSE score on full-time educational enrollment, we'll choose S1 GCSE PTS new as our independent variable. Before we run our logistic regression, we should run some exploratory bivariate analysis to get some answers about the relationship between S1 GCSE PTS new and S2 Q10. Because S1 GCSE points new is a continuous variable, we can run a two-sample t-test to determine if there is a statistically significant difference in the mean GCSE scores for those who have enrolled in education full-time after secondary school and those who have not. This, like all exploratory analysis, can help us determine whether or not it's worth fitting a logistic regression model for these variables. If the difference in mean GCSE score with respect to S2Q10 is insignificant, running a logistic regression wouldn't be the best use of our time, as our results wouldn't be significant. In addition to telling us if we're on the right track with our analysis, running this simple t-test will also provide us with the frequencies of those who answered yes and those who answered no, which will allow us to calculate the percentage of survey respondents who were enrolled and those who were not enrolled in full-time education. In order to run the independent samples t-test, go to Analyze, Compare Means, and Independent Samples t-test. We'll move S1 GCSE points new into the test variables box, and S2Q10 into the grouping variable box. You'll see here in the grouping variable box that S2Q10 is followed by two question marks. This is because S2Q10 is a categorical variable, and we'll need to tell SPSS what the two categories in this variable are. So we'll define groups. Group 1 is yes, which is coded as 1 in the variable, so we'll put 1 into group 1. And group 2 is no, which is coded as 2 in our variable. We can click Continue and OK to run the t-test. In the output window, you should see two output tables. The first is the group statistics table, which shows you the number of students who answered yes and the number of students who answered no to the question in S2Q10. You're also provided with the mean GCSE score for both yes and no, and the standard deviation for both of those groups. In the second output table, the independent samples test table, you're provided with the significance level for this t-test. This significance level is p is equal to 0.000, which is far below the significance threshold of 0.05, which means we can conclude that the difference in the mean GCSE scores between those who answered yes and those who answered no to the question in S2Q10 is statistically significant. And because we've just discovered that there is a significant difference between mean respondent GCSE scores, we know that there is a relationship between S2Q10 and S1 GCSE points new. So now we can continue on to fitting a logistic regression model to further explore this relationship. In order to run the logistic regression, go to Analyze, Regression, and Binary Logistic. In the logistic regression dialog box that opens, first we'll have to find S2Q10 and move it to the dependent text bar, and then we'll find S1 GCSE points new and move it to the covariates or independent variable text box. And now we can click OK to run the logistic regression. You should now have several output tables open in the output viewer. And now we'll take a look at them. The first table, called a case processing summary table, shows us that we have 9,705 cases included in this logistic regression, and we have 4,298 cases which are coded as missing. In our dataset, in the variable S2Q10, the category yes is coded as 1, and the category no is coded as 2. An answer of no, therefore, has been arbitrarily given a larger numeric code, because 2 is greater than 1. In logistic regression in SPSS, the variable category coded with the larger number, in this case no, which has been coded as 2, becomes the event for which our regression will predict the odds. In other words, because the outcome no is coded as 2 in the dataset, the logistic regression will predict the odds of a respondent answering no to the question of whether or not they are enrolled in full-time education. Because we are now predicting the odds of a respondent answering no, the answer becomes a success in our model, or 1. An answer of yes is a failure, or 0. You can see this reflected in the dependent variable encoding table. It shows us that the original values, yes and no, have been recoded in this logistic regression as 0 and 1. As you can see in your output window, SPSS gives you many tables, most of which you won't need to worry about. Here we'll just highlight some main points. The other tables become more useful when you do more in-depth analysis, but we won't worry about them now. The output tables in Block 0, beginning block, show the full-time education enrollment predictions before the addition of our independent variable S1 GCSE points new into the model. Block 0 shows us the odds of a respondent not being enrolled in full-time education without the influence of GCSE score. In the variables in the equation table of Block 0, we can see the odds of not being enrolled in full-time education. These odds ratios are presented as the XB output in this table. Here we see that without the addition of GCSE score, the odds that a respondent would not be enrolled in full-time education are 0.237 the odds that a respondent would be. In the variables not in the equation table, we see the predicted significance for the variable S1 GCSE points new. If P is less than 0.05, this table predicts that GCSE score will be significant, and that the addition of this variable will improve the fit of the model. Before we move on to the logistic regression that includes S1 GCSE points new, let's take a look at the information provided here. We can see that the predicted p-value for S1 GCSE points new in this model is 0.000, which means that it is predicted to be statistically significant. Let's move on to the Block 1 method enter to see what changes, if any, our independent variable has on the predicted odds of a respondent not being enrolled in full-time education. The omnibus tests of model coefficients table shows us the results of a chi-square test. This hypothesis test examines whether or not there is a statistically significant impact of GCSE score on the prediction of full-time enrollment in education after secondary school. In order to accept that GCSE score has a statistically significant influence on full-time enrollment in education, the p-value must be less than 0.05. And we can see here that at 0.000 it is less than 0.05, meaning that the influence of GCSE score on a full-time enrollment in education after secondary school is statistically significant. We can use the Cox and Snell R-squared statistic calculated in the model summary table to gauge how much of the variation in full-time enrollment in education is explained by this model, and therefore how well this model fits our data. In this example, the R-squared is 0.168. This shows us that 16.8 of the variation in educational enrollment is explained by GCSE score. We've calculated this by multiplying 0.168 by 100. This indicates that other factors are affecting a respondent's enrollment in full-time education. In the variables in the equation table, we can see that the p-value for S1 GCSE points new in this regression is 0.000, meaning that this variable does have a statistically significant influence on respondent enrollment in full-time education. As you can see, running the logistic regression is not a problem. As long as you remember to put the binary outcome variable in the correct text box in the logistic regression dialog box in SPSS, it's difficult to go wrong. However, the interpretation of the results is a bit trickier, and the interpretation is what you're really interested in. As we said earlier, we can easily see that the relationship between GCSE score of the respondent and enrollment in full-time education is significant, which is shown here by the significance level being less than 0.05. But what is this relationship? For every 1 point increase in GCSE score, the log odds of someone not being enrolled in full-time education decreases by 0.010. This doesn't mean much in terms of interpretation, which is unfortunate because logistic regression actually conducts the analysis on these log odds. A better way of interpreting this is by using the odds ratio, which is included in the XB column, this final column of the table. In our example here, the odds ratio is 0.990. Because S1 GCSE points new is a continuous variable, we can say that with every 1 point increase in GCSE score, the odds of not being enrolled in full-time education after secondary school are multiplied by 0.990. Because 0.990 is less than 1, any odds being multiplied by 0.990 will necessarily decrease. Therefore, as GCSE score increases, the odds of not being enrolled in full-time education decrease. Young people with higher GCSE scores are more likely to be enrolled in full-time education after secondary school. This difference by GCSE score is subtly reflected in the mean GCSE scores for S1 GCSE points new that we calculated before running this logistic regression. The mean GCSE score for respondents who answered yes to full-time enrollment in education is 432.8466. The mean GCSE score for respondents who answered no to full-time enrollment in education is 290.7032.